Okay, so welcome everyone. So tonight we're going to do kind of a continuation of our rope discussion last week. Let me share my, there we go. Um, so I think, so mostly this week is going to start with, I had a notebook where I'd just been playing around with rope. And we're going to go through that, explore that. And then Ted was going to, has read through the couple of the papers that were referenced in the document. And we may jump into those if we have time this week or slide them off to next week, just depending on how things go. This is going to be, so it's really just, it's a Python notebook. It's looking at the code. It was my exploration of rope. And so I don't know how this will go. People, if it's interesting, we can slow down, make sure you ask questions if you have any questions. But also if it's not that interesting, we can quickly roll on to Ted's presentation. So, okay. I think we need just to a quick, let's see which was the one that had kind of the coverage of rope. I think this is the, so I'm not going to go through that. That was last week. But the quick summary of RoPE is rotary position embedding. It's defined by these equations. They're basically saying that the tokens with the position embedding are derived by the weight matrices, and then this complex, e to the complex number, does a rotation that is proportional to the position of the token. And the similarity function that we use for attention between two tokens at two different locations is a function of just the difference between the tokens, the difference in position between the tokens, times the dot product of the two. So anyhow, described by that. One of the key things is you add absolute positioning with your rotation as you define the tokens, but the similarity is by default is the related as a function of the relative position of the two. Okay, so that's that. What I want to do, so this was the notebook that I was going to go through. So just an exploration, I just kind of jumped around and had questions about different aspects of it and just tried to organize it. So we'll go through and just talk some examples of things in high dimension, what that looks like. I want to look at the original additive position embedding, how that worked, and then introduce the rotary position embedding. Look at using how the weight matrices can do rotation of the query vectors. Well, I guess it can do rotation of the key vectors as well, but primarily looking at the query. Want to look at what attention looks like with rope over a sequence of tokens that have had the rotary position embedding, quote unquote, added to them. Last time we had the question about figure 2. What was that? What did that mean in the paper? And so I was able to recreate that. We'll look at that. Here, attention with rope, I don't recall the difference between those two. And then one of the questions I had was, is it possible to make this rope attention kind of less sensitive to position? It can be very specific. You can query at a very specific location, but I wanted to see, is it possible to query at something that's less sensitive to the position? Ted and I spent a couple hours last night kind of exploring and playing with that, so I can take a look at that. I also wanted to say, well, how does this compare to the old additive position embedding? So I want to take a little bit of a look at that. Softmax, how does softmax change these attentions that you get over a sequence? And then subspaces, I was also curious about, because in our Ted and I's discussion, we talked about like what are the subspace, where is the position embedding live, and where therefore must the kind of token embedding space live. And so I was playing around a little bit with subspaces. So that's kind of the high level overview. Does that make sense?
Makes sense. Given our track record, we should be able to cover that in about 19 sessions.
I know, that's the problem. Okay, so before I could play with high dimensional space, so here again, I've made references before that, like, I'd like to gain more of an intuition about how do things behave in high dimensional space. So to start out with, we talked about, we've been talking quite a bit about things living on this unit hypersphere. So created a utility that will just return a vector in a model dimension or D dimension space that exists on the unit hypersphere. I think that this distribution will give it kind of an even distribution over the surface of that hypersphere. Also created, again, need a little later, I wanted a transformation matrix that doesn't change the norm of the vector. I don't know what the correct term of that is. It's eigenvalues are all one or something like that.
What did you say, Julius?
So if it's real, it's a unit, it's a orthogonal matrix, and if it's complex, then it's a unitary matrix. So, you know, all the eigenvalues are one, and it preserves Euclidean norm. A rotation. It's a rotation in n-space.
Yeah.
Okay. And I think I got that. I did some tests to make sure that doesn't necessarily look like it forces them to be. It is a SVD. Is that by definition orthogonal? Oh, I guess it must be there.
Yes, and yeah, the U and V are orthogonal, and then the diagonal can be, the singular values can be any real number.
Right, right. So I made them all one here.
Positive.
So that's what these two methods functions are. And then I wanted to just look at, so again, some intuition, high dimensional space, similarity between any two vectors on that hypersphere is looking at the dot product of the two vectors in hyperspace, looked at 1,000 of them, and looked at similarities. So the mean between those is 0, so they're basically orthogonal, with a distribution, standard deviation rather, of this value, which I don't remember why I pulled this up, but I seem to remember something about this, that the standard deviation of those random vectors is going to be around the square root of the dimension of the hypersphere. I don't know, Julius, have you seen that before?
That sounds right. 1 over that, because the variance is like 1 over n, where n is the model dimension. So the standard deviation would be the square root of that. So that's your expected, that's your 1 sigma point.
Yep.
Yeah, and that variance comes from, if you imagine you just have an n-dimensional string of numbers, like whatever, between 0 and 1, and like 0.5 or whatever is the average or something like that. And so basically, the longer you make your dimensionality, the when you just do your standard, multiply them all and then sum it and take the square root, right? So the more things you have, the more they're just gonna keep adding and adding and getting bigger and bigger.
Right. Okay. The other question I had is, so if I had two vectors on there and that unit hypersphere and add them, what does that look like? And so, 1.4. That's kind of more important when we're adding, doing additive embedding instead of rotational embedding. Also, remembering superposition. So when you have these high dimensional vectors, you can actually, you can add them and kind of they both exist in that space. Julius, you had an equation I remember somewhere about the how many vectors you can record in a d-dimensional space. And it's because it's the sum of them. Originally, I think you said it was d, but because it was the sum of them, it's less than d. It was a square root of d or something like that.
Yeah, it just depends on where you draw the line. If you're willing to tease them apart, then you can, it's kind of unbounded, but if you really want them to be separable, they're like they don't overlap too much, so that even in the presence of noise, you can tell them apart, then it basically becomes the model dimension, which is the same as the number of exactly orthogonal vectors as you have. So,
right.
You don't really get a giant increase over the obvious ones, but you can push it. If you remember the pentagram and the what do they call it? The overloaded
Yeah.
superposition, they call it.
Yeah, I didn't get to recreate the pentagram, but yeah, that was a really interesting one. I actually kind of would like to recreate that because that was pretty interesting. But in this context, I just took two high dimensional vectors, add them together, and then I can use the dot product to say, is A in that sum, and is B in that sum, and is C in that sum, and you get kind of this answer that yeah, the dot product of that sum with A is kind of one-ish, B is one-ish, and with C is close to zero. So you can see there's a little bit noise there that's getting added in, but it's kind of close. And that 0.016, I wonder how that compares to. I'm not sure how what I would expect to see there. 0.016.
I don't think you can draw any conclusions because C is a single number. You didn't
Yeah.
average. If you averaged
Yeah.
hundreds of them, then you could draw a conclusion.
Maybe see that. Yeah. Interesting. Okay, that's a good point. And let's see. I was just adding more and more, so up to 100 vectors, a random unit, vectors from the unit hypersphere. Just adding them and then just see what the sum looks like. I couldn't explain this roll off. The more I add, the less it's growing. Does that intuition work for anybody?
Yeah, because the more and more chance of collinearity, partial collinearity, or whatever.
Ah,
So by the time you get to 999, it's
almost
it's no
everything's already there.
longer likely to be orthogonal to everything that's come before it. It's much
Gotcha.
more likely to overlap with what's come before it.
So this should completely taper off then when you get
Yeah.
up to the model dimension size.
Yep.
Interesting.
What happens if you square it? Um, does it become more linear if you square it?
What do you want to do?
Just square what you're plotting. So right now you're plotting the amplitude of the sum, right? Um,
Let's see, plot the array. What's the best way to square that for?
NP dot square. I do not know. I would ask ChatGPT. Nice. Okay.
Nice.
So yeah, so the variance is growing linearly and the amplitude is growing, it's like the square root of the event.
Yeah.
Interesting.
That's-
Okay.
And why is it in two groups? Why do we see two?
I think that's probably just an artifact.
Ah, okay.
I doubt it's real. Yeah.
Oh yeah.
Yeah. So
Mhm.
let me also, I want to get rid of that square then. So this one should roll out by the time I get up to 512.
Well, it'll keep going up. It'll just go up, as a square root.
Right. It's never gonna be asymptotic. There's no horizontal
Okay,
asymptote.
okay.
It's just the square root of n.
Goes to the square root of n. Yeah, okay, I see. Okay,
Well, eventually we'll hit our 10H or our activations
interesting. Yeah,
touch rate somewhere.
yeah, all right. That's cool. Let's see, then I looked at superpositioning when I'm just adding vectors. This is 10 unit vectors, the norm of them. What was I doing here? So this is, as I get more and more, add more and more vectors in, what is my ability to pull out that the original vector, and it out to 4 it doesn't grow too bad. If it goes larger, it's still saying it's there. What if that
These are
would
1,000 long vectors, right?
512 is the dimension, model
I
dimension,
thought
I
up
believe.
top you said, oh,
Model
never
dimension
mind.
512.
Yeah. So if D is 512, you're going to be able to pack quite a few in there.
Mm. Okay. So yeah, yeah. So it starts to get pretty high variance then. I don't know where you'd say it's too noisy to be useful. Probably somewhere in this range, depending on how you're thresholding it. But
Yeah, like what your tolerance for bad luck of the draw.
yeah, yeah. Okay, so anyhow, that was just playing around with just some things in high dimensional space. So the original additive position embedding from the attention is all you need document was defined as adding the sine and cosine on alternating odd even dimensions. I think I've run all these, so I should be okay. So that's defined here. I tried to recreate, hopefully I recreated the equation correctly, add in sine and cosine. And I looked at how it changed. So this was something, when you add in this RoPE for this 512, the norm of the vector, because we had talked about, Julius, kind of liking the idea of RoPE, that it doesn't change the norm of the embeddings, right? The token embeddings. When you're doing additive, it's going to change the norm because it just, it adds a change that makes it bigger, as we saw. In this case, it added it, so the norm of the original X was, so what do I got? Unit vector V, I do the position embedding, I do it 1,000 times, and I take a mean of the 1,000. So on average, it changed the vector to size 16 from size 1, norm from 1 to 16. I was surprised by that kind of that much of the magnitude was going to be committed to position embedding. But I didn't see anything that scaled it. I mean, theoretically, you should be able to just scale how big that is. I don't know what would be a good value to choose. But anyhow, that's what I saw in it. So this is the VM actually is the vector plus the embedding. M is just the position embedding, the magnitude of the position embedding. So yeah, so a mean of 16.
So what was the amplitude of the, this is the additive sinusoidal modulation as used in the transformer paper?
Correct. Or at least that was my objective.
And what was its amplitude?
So here I'm printing the mean and the norm of just the embedding signal. And here I'm printing the mean and the norm of the embedding plus a random vector.
So the mean of the encoding vectors is 16.
Yeah, yeah.
Yeah, because as written, I don't remember exactly how it was done, if it was normalized, but each of the 512 numbers goes between -1 and 1 for sine and cosine. Now, yeah.
Oh,
So,
and you're probably going through just a small part of the cycle, because the way
yes,
frequency is modulated, it starts out really slow, and
right,
it doesn't oscillate that much. So you've got this
right.
huge component because of the way you're.
But the high frequency ones oscillate a lot, and some of them make it all the way to 1 or -1, and that's where the 16 comes from.
Well, those should be zero mean, shouldn't they? The ones that are oscillating a lot.
This is not taking the mean over each coordinate and then summing it. It's summing it and then taking the mean.
Yeah.
So you're going to have ones that are close to 0. You're going to have ones that are positive, ones that are negative. If you didn't take the absolute value or square it, you're right, they would cancel out and you would get close to 0. But by taking the norm and squaring it, then you get some big positive outliers, some big negative outliers, and it ends up pulling it all up to 16.
Okay. So
And
you'd probably have to plot them to see how crazy they are.
that's this.
That's
So
positional encoding vectors.
yeah, so this is it. Well, this is encoding vector plus a random I guess it's actually a vector, so like a token embedding vector, and then for 1 through 10,000, plotting the plotting the norm of the vector plus the embedding. So how does the embedding, how does the magnitude of the vector change over time?
Yeah. And I'd have to look to see whether or not they actually scaled those position embeddings. They might have divided it by something to make them
Yeah,
smaller.
I kind of felt like that. I'm not going to say I did an exhaustive search, but I couldn't find where they talked about scaling it. To me, it would make sense to scale it because it seems like, if you're using dot product for similarity, the similarity is going to be dominated by the position here. It's almost like you could scale it to get a relative weight between position embedding and token embedding if you're using dot product.
And it's not that important since people have moved on to RoPE anyway. So
Yeah, right. Which is the next one. So in RoPE, then it's a multiplicative position or rotational embedding, and we use this theta I, which again is very similar in terms of this 10,000. I don't know why they picked that, but it's the same one that they picked in the attention is all you need paper. And I tried to recreate this here. I used formulation that most closely match this definition. So I is from 1 to d over 2, d1 to d over 2, and then plugged in the I minus 1, 10,000 to the power of minus 2, I minus 1 over d. So I tried to recreate this same formula. And then I take the even positions times cosine minus sine, and let's see, oh, no, excuse me. Yeah, the position is the even times the cosine minus the odd times the sine, and the PE2 would be the odd is going to be the even times the sine plus the odd times the cosine. And okay, so given that function, we're looking at the magnitude of given a unit vector, do a rotation. So RoPE applies the rotation to this vector v of this many positions. And I just rotated it through the first 10 positions, and plotted out the norm. So as expected, it doesn't change the norm of the vector when it does the rotation, right? Okay, so I wanted to play around a little bit with then how these embeddings, positional embeddings, behave when you're doing dot products. And at first I thought of it from the perspective of rotating the query and key vectors. Later on I look at it using the weight matrices, but for right now I just use the key and query vectors. So a lot of this stuff I'm doing, I just pick a random vector, and the query is going to be 100% match on that key. So the norm of these unrotated vectors is 1, as we would expect. And then what I did is I said, okay, well, let's rotate both of these to the position 0 using RoPE. And again, the dot product is 1 as expected. And then we started putting a little difference in it. So 0 is still going to be rotation 0, the key is 0, but now I'm going to rotate the query by a position of 1. And you can start to see a little bit of drop off. Do the same thing, rotate the query by 10, and it gets more drop off, etc. And just to prove kind of that, again, it's even though you add absolute encoding as you generate the keys, the dot product is related just to the difference between the two. So we go out to position 10, we got a query at 10 and a key at 10. These should match, and yep, sure enough, 100% match out at that point. Does that make sense? Any questions? Okay. Here, I think I just did the same thing. I just did a little bit further out, so we're out at 100. So going from 110 to 110, you get the 1 as we expected. And then when there's a difference of 10 between them, you get 0.68, which is the same one we were kind of based on 0. So again, it's kind of translation and position independent. It's only the difference between the two. Later on, I play with a little bit using this rotation matrix. So in the paper, they had 2 references, 2 implementations of it, I think. One was this diagonal matrix, and then they later decomposed it into a more efficient computation here, which is element-wise multiply between the positions and cosines, and kind of slightly permutated vectors and the signs. So that's a second implementation. So I implemented the first one, a slightly different notation. I didn't use the 1 through d over 2, but it's basically implements the same thing. And I just wanted to prove to myself that this matches. So pick a unit vector, and rotate it through n degrees and make sure that the RoPE implementation matches the rotation matrix times or dot the vector. And yeah, sure enough, they're all the same. I also wanted to see that the rotation matrix is invertible. So you can rotate forward, you can rotate backwards. And so I just did a rotate forward, rotate backward. So if you rotate it, let's say XR is rotated forward 1, and then XRR is taking the rotated 1 forward and rotating it back, and then so it should be the same. I happened to just use 1, but you know, any number should have worked. Okay, and this, by the way, Ted, I think you had a comment last night about the keys and the queries having opposite sign. I think that the point is that queries will reference back in time, and so that's where you do that rotation in the negative direction to attend it to earlier tokens. Oh, you're on mute.
Yeah, so I was having a little trouble yesterday, but yeah, if you rotate both of them 30 degrees, say, then they're rotated the exact same amount, and so then the dot product will be as if you didn't rotate either of them.
Right.
But what only matters is the difference, n
Right.
minus n, like you showed above. So
yeah.
For whatever reason, I was having difficulty with that, but
Okay.
I'm clear on that now.
Any other things we want to play with on rotary position?
I think it's cool to see it concretely, right? So we're talking about RoPE, but you're showing that, like, hey, if you dot identical embeddings, query and key embeddings are not necessarily identical, right?
Right.
So the query for dog and the
I'm
key
just
for
searching.
dog are not necessarily identical. But if you
Yeah.
just assume they're identical, then you get a flat out 1.0
Right.
when it's in the same position. And when they're 10 apart, it's 0.688 or whatever you said it was.
Yeah.
So basically that shows that if what you cared, I don't know, you may have some more stuff coming up, but if what you cared about was, I want the word that's X many words before me, then theoretically the model can learn, oh, for 10 words before me, I'm looking for exactly 0.688. And it can devise a calculation that extracts exactly that.
Right. Oh, this was interesting. I just checked chat. Morales said that the base of 10,000 was chosen with a hyperparameter search. That's interesting. My suspicion would have been that it was related to what was viewed as a reasonable window at that time, context window.
Yeah, I was going to comment on this later when we get into some of the other stuff, but basically, I'm pretty sure you want 10,000 to be such that for your context, you don't go through more than 1/4 of a period
Okay.
for your slowest moving um, portions. Right. The
Right.
high frequency portions are going to go through many, 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 many periods.
Right.
But your slowest moving one, if you're at 2048, then 10,000 guarantees that you move less than 1/4. And so for that one, it's very straightforward to extract because it's monotonic.
Yeah.
Right? All the higher frequency ones, you have to say, well, this particular value could mean this, or could mean that on the way back down, or could mean one period later, but everything will have not just one value per period, but actually 2 values per period. Does that make sense?
Yeah.
So, and the
So
two
that's why you're
values
saying
are
a
not
quarter.
the
Yeah.
two values are not evenly spaced. So like if you were looking for 0.99,
Oh,
then they're going to be
right.
very close to each other, and then you're going to go almost an entire period and then have two very close to each other, right? And if you pick something that's closer to 0.5, that's when they'll be approximately evenly spaced apart. Or no, 0 if it's between 1 and -1. At 0, they'll be about evenly spaced apart.
Right.
But if you pick anything that's not near 0, they're going to come in sort of pairs, as it were. And that just occurs to me as not the easiest thing for just something that only knows how to do matrix multiplication and addition. Like,
Right.
for multiplication addition, how do you decode that? So that's why I think having your slowest ones be less than 1/4 means that every value is unique. It's monotonic.
Hey, Roger, your comment that it also sets the window, that's very interesting. It means we've got another case of conflated uses. So one is to not, alias, not to go around and to have a good, range of monotonically varying encodings, but then it also does set the window. So if you went faster, then you would get a narrower window of let's say capture range for the key. But of course, you can always add another vector at another position. In other words, you can just add vectors at different positions to synthesize a wider capture range. But let's say it sets your minimum capture range window. That's the interesting conflation there. We can.
I don't
Yeah,
know
what's
if this
interesting.
is true, but like if you doubled your context length to 4,000, my first intuition would be change that base to 20,000.
Mhm.
Double it.
Yeah.
Yeah. And that's going to stretch out your minimum
Well,
tension window.
yeah, and that this is the paper, Ted, you'd read through the positional, what was it, interpolation, where what they do is instead of kind of extending out that 10,000, instead what they do is they increase the sampling on the high frequencies.
Well, that's a separate thing. That's for when you want a longer context than what you trained on. But I'm saying if you're
Right.
willing to train on 4,000, my gut tells me the first thing you should do is if you double your context length, you should double that 10,000.
Yeah.
So again, such that your slowest moving part of your positional embeddings never goes through a full quarter. Yeah.
Interesting. Yeah. Okay. Very cool.
By the way, if you still have that diagram, you can see where there's that one part that only seems to go through a
Yeah, I
quarter
do
phase.
have that. I don't.
That's fine.
Yeah, we'll get to it. I think it was down in the making it less sensitive, the conversation you had. Okay, so my next thought process was that, okay, well, this is Q and key, the query and the key. But actually the embedding, as I understand it, is added at the bottom of that, the transformer, where it's added to the original token. So it's added before the Q the weights for those query and key matrices. So generally, the key is WK times X sub I, and query WQ times X sub I. So what I wanted to do is say, well, okay, to me it seems like it would make sense that a query might say, look a token before me or 5 tokens before me or something like that. And so the rotation was actually going to be done by the query matrix. Can they do that? And so I wanted to explore that. So basically what I did is, okay, so here we have a X is a unit vector. This K is going to be just this unit transformation, just a random, what do you call it? Julius, you had a term for it. Multiplying by this does not change the norm of the vector.
Random rotation?
Okay.
Yeah, these are real, so this is an orthogonal matrix.
Yeah, orthogonal matrix, okay. And so I first set them just identical, and then I think, let's see, I took just a short sequence at position 0, 1, and 10. I used the WK to generate these after the token had been added. So this has the original X vector up here, just a random vector, and it's been rotated by position 0, rotated by position 1, rotated by position 10. So X has the rotation in it. And then I'm going to multiply by WK, which doesn't do any rotation right now, right? It's just this transformation, which happens to match WQ because we want the Ks and Qs to match up. So I rotate and get the key at position 0 by rotating the embedding, the X with the 0 position embedding times this matrix to get the key at 0. Same thing, key at 1 and key at 10. And same thing for query. I don't know why I didn't do query 1, but I did 2 of them there. And then I said, okay, so the query generated by this weight matrix at position 10, when it attends to the key generated at position 0, what do I get? And it's a less than 1 number. And if I take kind of a self-attention, the query at 10 times the key at 10, or dot product the key at 10, I get the 1. So that is kind of what I would expect, right? Because there's no rotation in here. But what I was looking for is I'd like to have a weight matrix Q that will, by definition, when you multiply it by, X sub I that's already had the embedding, it'll attend to K sub I at some position in the past. Okay? So that's what I was wanting to do. So what I did, let's see, the first thing I did is just prove it, I guess, without the weight matrix. I take a query at position 10, I rotate it minus 10 positions, and so I get query 10 back 10. And I want to say that is the same as, let's see, query at 10, embedded, what was I doing here? This is rotating this guy. Oh, this is rotating this forward 10. So the query at 10 is whatever this one is rotated forward. That's just kind of the invertible. Rotations are invertible. But I also wanted to prove that this comment here is wrong, but if I have the query at 10 rotated back 10, so that's from up here, and multiply it by the key at 0, that should be, oh, sorry, it was on this one. So query at 10, rotated back 10, is it the same as the query at 0? And yes, it is. That's this one. So if
so if your key embedding matrix is the identity matrix, and your query embedding matrix is the RoPE -10 matrix, then you will get the strongest match on tokens that are exactly 10 positions before you.
Right. So this is just doing it by rotating the key vectors. Now is when I get to what I was talking about earlier, is I want to make the query do the rotation backwards. So I took the query, so that's the one without, the highest signal would be on self-attention here, right? But what I wanted to add in is take that and rotate it back. So I want this WQ to create queries that automatically attend to positions 10 positions earlier. So now I do that. So that's the matrix that I came up, the weight matrix. And I dot product that with my 10th position. And that should be the equivalent of, I just coming up with a name here, but it's the query at 10 back 10. And again, it should be that if I use that query with X0, I get a match, and with X10, I get not a full match. Does that make sense? I might have messed that up a little bit in describing it, but basically, this is how I took a weight vector or weight matrices for a query that would match the key at that position, and said, instead, I want you to always look 10 positions earlier. I kind of added that into the weight matrix. And this thing just repeating it at another location, just because this should be kind of position translation independent. And yeah, it is. Not sure why that one, I'm not going to go down this rat hole, but that one should have been the same as that one. Does anybody see the mistake I made there?
Yeah, you went positive 10 instead of negative 10, right?
Oh, right, okay. Right, okay. Anyhow, so that was just, I wanted to explore how it could get embedded into the weights, not embedded, learned into the weights, and it seems to be that way. Okay, then I wanted to play with just how attention
So sorry, Roger, just pausing 1 second here. So just to be clear, what we're saying is if you're a transformer, if you're an LLM, and you're trying to learn English language, and for some reason you really wanted to be able to attend to the word exactly 10 words before you. I don't know that that's actually something that comes up in the English language that often, but let's just hypothetically say, that your transformer your LLM does want to attend to a certain number. Maybe 1 or 2 is more common than 10, but it wants to be able to do that operation. Then basically what you've shown is if you're using RoPE embeddings, as it's trying to minimize its loss, as it's learning over, trillions of tokens, basically it can learn a query matrix that includes basically the -10 rotation in it. And if it does that, if it learns that particular meaning for the Q embedding matrix relative to the key embedding matrix, then you're gonna see whatever, where if you have the same word dog appearing at previous token positions, the strongest match will be at 10 back, where it'll be 0.9999, essentially 1.0 times whatever the normal dot product is. But any place else where the word dog appears will be attenuated by that RoPE pattern, whatever it is. I don't remember what it is, but 0.9 for 1 position off, 0.85 for 2 positions off, and so on and so forth. So you can guarantee that the token 10 positions back will have the highest attention score.
And you can add them up, but I can't speak. Somebody's raising their hand. I have to wait. And I can't find how to raise my hand. I can't.
I think Roger did that accidentally.
Yeah, somehow I raised my hand.
Okay.
Yeah, but I wasn't going to stop for me. I don't even know how to lower it.
Well, so anyway, so just adding to what Ted was saying is that let's say you're at this position and you're you can set the rotation to look back here. Well, you can also add that to to the rotation to look back here and to look back here. So in other words, you can add up those rotations and be looking for everything in a particular range. So if you're a noun and you're going to accept adjective to the left and the right up to, let's say, 3 tokens away, then you would just add those rotations together because, it's a sum. Your dot product will be the sum of the individual dot products. And so it doesn't matter which one will fire, you'll get attention because they're all in there. So that's kind of a neat thing that the query can do. They can look for any rotations.
So,
I think you'll
Julius,
get a little bit of noise. Julius, you'll get a little bit of noise, but it'll work.
Let me I just turned off my air filter. Is that better?
No. I'm saying when you sum all of these matrices, there will be a little bit of noise you get.
Yeah.
just like that
will not
superposition.
all be equal because the ones in the middle will be a little bit higher because they're going to get contributions from everybody around them, whereas the ones on the end will tend to get only half as much contribution because on one side they're going to get contributions but not the other. Because right, we said that like the one you really want is going to be 0.9 and the next one's 0.85 and then the next one's 0.8. So it's not like you just get a 1 and all zeros, like it's a perfect notch filter. Right.
It's like a window function.
Yeah, exactly. So what I'm saying is if you picked those 10 windows and you did them all together, then what you would see is a little bit of a shoulder around the 10, and then it would still be highest in the middle of the 10. But it would be approximately a plateau that's 10 wide.
I think it can plateau. I think that the edges of the window are going to look like your minimum window, but you can get a flat plateau in the middle because you're summing those. Just think of it as summing these overlapping windows, and the minimum window is set by that 10,000. But I think if you add all of the vectors in the middle, once your window that you're synthesizing is much larger than a minimum window, I think you get a plateau. Unless I don't know.
Oh, I see what you're saying, but I think the windows are actually quite broad because RoPE spreads out over your full context length 2000. So these are very broad.
So they're not very selective.
Yeah, these are not notch filters. These are the opposite. But they have their peak where you want them.
Mm-hmm.
And then what happens is softmax tends to promote peaks and suppress anything that's not the peak.
Mm-hmm. And doesn't it depend on your thresholds, your biases? Because, as you get towards the edges of the window, you have to have a lower bias in order to fire your activation.
Well, we can talk about the activation. Softmax itself does not care about a linear constant offset.
Mm-hmm.
It's insensitive to a DC bias.
Yeah, that'll get normalized away.
Mm-hmm.
Okay, you guys stop talking. I'm gonna have to go on. I was gonna try that additive. I didn't do that additive, but I'll add that to it. That'd be interesting to see how that works.
Mm-hmm.
Okay, but I did find the source of that matched up. I had forgot to calculate K110 with this vector X 110.
But so again, what you're doing is you're proving that there is a Q and K matrix that the LLM could learn that would allow it to select the word 10 words ago to a certain extent, irrespective of what that word is.
Right.
You might need to have your word embeddings sort of gamified so that there's at least like a guaranteed 1 in some position, right? If you knew that the 512th float was always a 1, then you can basically just grab that 1 and apply the rotary stuff just to that value, and then you know you're going to get the rotation and nothing else semantic.
Cool. Yeah, just a position marker, basically.
It's a dummy. It's a constant input, regardless of the token.
Yeah.
So that's good because we ultimately want our LLMs to be able to calculate the word before me, the word 2 before me, 3 before me, 10 before me.
Mm-hmm.
Okay.
And if it's English, it'll want the adjectives more in front of the noun, and if it's Spanish, it'll want them more behind the noun, so you can get these different weightings.
And because it's causal,
Right.
it'll have to actually be the other way. It'll always have to look before, but it'll be the adjectives looking for the nouns that they go with, whereas in English, it would be the nouns looking for the adjectives that came before it.
Okay.
Yep. Okay, I almost got that, but you guys didn't talk long enough. Okay, so so then I just started thinking, okay, so what does this look like when I have a whole sequence of them? This one I realized afterwards. So here what I'm doing is just coming up with a sequence of 1,000 embedding vectors. And then I'm adding the rotation, position, encoding into it. And then I'm querying with one of those to see how it matches to the rest and just plotting it. So it basically is very high. It's 1 for the position 0, and then low for the rest of the positions. I did realize later in the game that my examples mostly start from the left and go query forward in time. That should be the same as querying back in time because it's symmetric. That just happens to be in the figure 2, they did it forward in that direction like that as well.
Oh, yeah.
That's anyhow, but yeah, it just shows that it's unit vectors dotted together. Random ones are the similarity is low. If I pick one, this is kind of the same thing, except I'm picking one in the middle and plot it. You can just see it grabs that one out of the middle.
So word embeddings are not random, but this shows that the odds of you getting a spurious, really high dot product are very low.
Yeah, yep. And by the way, this doesn't have softmax. I explored that later. We'll look at that. This is just a dot product similarity, not softmax overhead. Okay, so figure 2 in the RoPE paper was this one. And we weren't exactly sure what that was telling us. And I think I ended up recreating that. So instead of 1,000 sequence of different tokens, I'm going to have 1,000 sequence of the same token. The only difference between the positions, the tokens in the sequence, is the rotary position encoding that's been added to them, quote unquote, added to them. So that's what I did. Pick a vector, whatever vector, make, in this case, 250. I think figure 2 was 250 sequence, and add the embedding to it, and then just pick one of them as the query, the first one. And this is the attention matrix, so dot product between the query and all the vectors with their embedding, position embedding. And it looks like this, which looks kind of similar, but if you look at it, it's not identical to that one. It's just kind of similar-ish. It goes down from 1 down to 0.35. Is that about some 20? So
Roger,
yeah.
Perhaps they just picked a random vector like you did, and so they got a different one.
Yeah.
But another thing I was thinking that they might have done was picked all ones and then normalized it to be unit length. And so you could try and see if that recreates their diagram.
Yeah. Ones.
I know that's
No,
pretty
but
different.
that looks a lot cleaner. It's interesting.
Yeah.
So that's something that's spread out over all the dimensions. That doesn't match their.
No, so they must have just picked a random
And have to
like
be different. Yeah, and I said, well, that's okay. That looks different. What if we start with different vectors? And yeah,
Yeah.
sure enough, you get kind of the same, what do they call it, exponential or whatever, decay, but um,
Actually,
each one's different.
is the red the average?
Yeah,
The red
average
looks a
over
lot like
10.
my all ones.
Yeah, it does, doesn't it? This one's a little bit smoother. I might have just not done enough too.
Because basically, right, the all ones gives equal contribution to every
Yeah,
one of your sines and cosines,
yeah.
which averaging over a bunch, I think would do the same thing. It would give equal contribution.
Yeah. We're coming back to that while that's running.
It's going to chug for a while.
Yeah, I didn't realize it was going to take that long. Okay.
So all the parameters were the same as in the paper?
Yeah, I think so. I think I got the equation right, 250, right? It was 250 positions approximately.
Because it looks
Hey,
like
there's a question in the chat there too. You might want to
Okay.
look at.
Would the decay be the same across dimensions? Well, we're not really looking at the dimensions. I did that a little later. But here we're looking at the norm we're looking at the dot product between the two vectors with different positional embeddings.
Right. So the x-axis on figure 2 is how far away the key is from the query, assuming that they're otherwise identical embeddings, which
Yeah.
would have a dot product of 1.
And this relative upper bound, it says relative, so I don't know why they normalized to 20, or I don't know how they picked this range, but this would be a function of what this peak here would be the norm of the vector squared. In my case, it happens to be 1 because I'm doing unit vectors on the hypersphere, so it shows up as 1.
what if they took a log?
Okay, there you go then. So the red is the mean of 100 runs, and that looks a lot like that one, doesn't it?
Yeah, I think so.
So it's kind of like in this case, on average, we hit all the dimensions equally, right?
Mm-hmm.
Just each of the particular vectors didn't hit it equally, but since we got 100 of them, it kind of averages out close to everyone hit equally. That's very interesting. Good insight, Ted. Okay, so that's figure 2. Let's see, what did I do here then? So I wanted to explore when there was random tokens, a lot of random tokens, but occasionally a token that matches. So this is like, dog occurring in the sequence of 1,000, it occurs 10 times. What does it look like when we're searching for that? And you can see that, so this is, I'm running the query at position 500, and I place these at every 100, 10 of them at every 100. And so when I run this, you can see you get the strongest hit right at 500, but you also get these little hits off at the other numbers. And my guess is we should see this matching this curve pretty closely.
You're basically sampling every 100 points off of
this one, yeah.
Off of one of those curves, not the red average, but off of any one of those curves.
Right.
So if you look at figure 2, figure 2's not monotonic. It squiggles up and down.
Yeah, quite a bit.
And then I was noticing that on your plot, you have those spikes every 100, and I was like, oh, look, the spikes are not, if you scroll down, the spikes are not monotonically. You see how like
they go up and down.
900 is more than the 700 or whatever?
Yep.
So I was like, oh, yeah, that's right. I wasn't expecting that at first. I was thinking it was going to be more like a Gaussian where it was just nice and predictable.
Right.
But it's a little bit more random than that.
Based on what your random vector was and how it lines up with the position embedding vectors. Yeah. But it should be, like you said, these should be sampling from this distribution, basically.
Exactly. Yep.
Okay. So here I just did, this is showing the relative positioning. So this is a query that would have matched here. but then I added a rotation into it of -100. So it picks up the token that was 100 earlier instead of the token, kind of the self-attention token, as we did expect. Again, nothing unexpected, but just visualizing that. And I did also try, well, what if I pick one that doesn't match either one? And you get something like this. So these two, I was right in the middle, so I sampled both of them. And again, I think that those all sample this line, or more cleanly this line. They sample this distribution, and it would have been like 100, so 0.4 or something like that is, yeah. So around, whoops, the peaks would have been around. Well, these are a little bit higher than that. This is because these are only 50 off. These are only 50 off. So at 50, it's like 0.5 or something like that, sampling somewhere around 0.4 to 0.6. And these are closer to 0.6, but make sense? Any comments, insights? Okay, so this is the thing Ted was helping me out with last night, and that is, I was thinking, but it seems like queries, you would often, it's kind of nice that you can pull out, you can pull out that one very specifically, but it seems like it would make more sense to have a broader search, kind of anything out in this range would feel right to me. And so I wanted to see, like, how can we make the query be less selective? And we had this idea that because the embeddings, the low dimensions are oscillating really fast and the high dimensions are oscillating more slowly. Here's the map that kind of reproduces, I think Ted posted one similar to this. So these are the low numbered indices into the dimension space. They oscillate a lot. This is over a sequence of 10,000. So the sequence length is along here. And then out in this dimension, so the 500, 512 dimension doesn't rotate near as fast. So we had this idea that you could make it less selective by somehow ignoring these high frequency ones and just paying attention to the higher ones. And so we tried that. We did a, let's see. Oh, this is just the answering question, kind of where does this space live? And one of the things I got out of this is, I mean, these dimensions, these position embeddings, they land on all dimensions. So it covers the entire space here when you're in a long sequence. But if, Ted, you had kind of suggested that the two modes really are either something nearby or anywhere. It's kind of, that's the way the language models work, right? So if you're anywhere out in here, well, long sequence. So now if you're down in the bottom, you've started to rotate some of your higher dimension. That's kind of like taking the whole vocabulary and just rotating it to another space. But all the vocabulary is in the same area, so the relationships are the same. And that doesn't interfere between those token embeddings. It is just these little differences that will reflect the small rotational one. So it's just this. So you probably can, you can use a lot of this if you're only referencing plus or minus a little bit, say 100 tokens or something like that. You can use a lot of this space in here for your embedding and not collide with a position embedding subspace. But you may want to stay away from this lower order stuff that you're using a lot for small relative position embeddings. Does that make sense, Ted? Does that line up with what we talked about?
Yeah. So the key thing to remember is that RoPE embeddings are not inserted at the bottom of the model. RoPE embeddings are applied at every layer conceptually after you have already calculated your queries and your keys. So you calculate your unpositional queries and keys just by doing, weight matrix times your x's. Then you apply the RoPE embeddings there, and you do that process at every layer. And so the RoPE embeddings cannot get sort of transformed and passed up to higher. Well, they can be transformed and passed up to higher layers, but it's not dependent on those at the higher layers. At the higher layers, they get their own de novo rope embeddings multiplied in every single layer.
That was one I still didn't. Did you ever find a reference for that? Because I didn't understand this to be. I thought it was just like the transformer document where they
No,
where they
it's
add the positional encoding right at the bottom.
yeah.
They don't
So
show the key and query calculation.
Well, that's in here, but the position embedding, you're saying with RoPE they changed it. They moved the positional embedding from here up into this space, inside this yellow thing.
yes, it happens. It happens right before the dotting of Q and K.
Okay.
Can't it happen at the input? In other words, where it says input embedding. So, in other words, can't you apply it to the embedding as labeled in this figure? And then, but then your case
You could do that, but RoPE doesn't do that.
Okay. Well, let's
Okay.
we're going to roll over anyhow here, so maybe we can look that up before the next one.
Yeah, I'm up here.
So this is from actually the Alibi paper. I'm going to post it in the chat.
Okay. It talks about that then, huh? Okay. Let me go ahead. We got about 15 minutes left. Let me go ahead. I don't think I can make it through this, but maybe I can. So this is, I think I've stated this then. So our theory is that you can, the small relative differences you just need to avoid in this area. And in here, it just creates kind of a bias to the vocabulary, but it doesn't really interfere with the token embedding in that space. So here we decide, we feel like the intuition is that the precise location's in the low bits. And so what we tried then is, here's our reference, which is just a queried back 100 like we've seen before. But what we're going to do here is we're going to take that same query matrix that we had, or query vector that we had, and we're going to zero out the first n dimensions and spread dimensions, where spread right now is 260. We're doing that to the query. And then the other thing we did is we actually said, well, it could be also, you could zero out the positional embedding in the key as well. So you can either make a query that's less sensitive in terms of what it's going to ask, or you can make keys that no matter what you do, however you query them, they're not going to be very position sensitive. And it works both ways. So this is what we plotted. So it worked. The reference spike here is using the full query to match the key. And one of these lines, I don't recall which, I used slightly different spreads. So I zeroed out the first 260 dimensions on this one and the first 250. So this one should be, the higher one is where we zeroed out the keys. So as we were creating the keys, as we were adding the embedding to the keys along the way, we didn't embed position information. And here on the lower one, which had the higher zeroed out bit dimensions, so it's a little lower on this search. That was just, so the keys had their full embedding, positional embedding, but the query essentially was ignoring the lower dimensions, so ignoring the fine resolution position information. So that had kind of what I was looking for. Mind you, this should have been, over on the right and all looking back, but here it's just centered over 100, but it didn't match that.
Right. So what you're showing is the attention scores if the keys are the repeated word over and over again, dog, 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 dog.
In all these cases, yeah, it's the
right. So now you can see there's some slight differences But if you had one word that was a really strong match, dog, and you had another word, tree, that was a very poor match, then basically, no matter where the word dog is, it would be somewhere between 0.48 and 0.52 times the maximum possible dot product with the word dog.
Right.
But if you imagine that the word tree had a 0.01 dot product, then it doesn't matter whether it got a 0.48 or a 0.52. It's going to be way lower than the word dog anywhere the dog appears in this window.
Yeah, that's going to be more like this back here where we're just querying random
Right.
random vectors, right? It's
Except
gonna
in
be
this
down
case, it's not based on position, it's based on semantic
Right.
content.
Yep. So
So
that was cool. That's what I was
yeah.
looking at.
So before you proved that transformer could learn a set of weights that would always find the word 10 earlier. And then this is saying this would find the best semantic match anywhere within the nearest 250 words.
That's a good way to think of it. Yeah. Yeah, it allows you to shift maybe a little bit more into the semantics and away from position.
Mm-hmm.
Yeah. You know, you could also do the opposite, I suppose, is that you could make it, if we zeroed out not this position, but zeroed out the higher side, you might be able to make it very position dependent and not semantic dependent.
Mm-hmm.
Yeah, which is interesting. Let's see. Oh, yeah, Ted just wanted to see this for a longer sequence. So this is just the same graph, but for a longer sequence. You can see it continues to taper down over time.
So now, in theory, if you had two words that kind of matched, then a puppy near the middle where the peak of the orange and the green is, versus a dog that's thousands of words away, even though dog is a better semantic match, it might not be able to get a stronger attention score than the puppy that's really close.
Yep.
Right. So although we're looking for the best semantic match, with rotary embeddings, it's still the case that words very far away tend to get downvoted even if they have good semantic matches.
Yep. And we can make this, I think you can make it as flat as you want, although,
yeah, if you just keep zeroing out more and more dimensions.
right. But then you have less and less available for your
semantic
your
matching.
Yeah.
Yes.
Okay, this one, this is a different thing that I was trying to do. I'm going to skip over that one, I think, for right now. I was basically trying to find out if the similarities between vectors are captured in the lower order dimensions. But I didn't really get a very clear answer on that, so I'll skip that one.
Yeah.
Okay, here's an interesting one. So I said, oh, well, that's all cool. So I've got this little code that looks, for attention over a sequence, right? How does that work? If I stuck with the positional, the additive embedding, what does that look like? And it's interesting. It doesn't drop so it's not as selective. This doesn't go down as far, but it does go down. It does have kind of a similar curve. It seems to be a lot smoother, which I guess is probably because I didn't use the ratio between position embedding and semantic embedding is like 16:1, right? The positional embedding's 16 times bigger than the semantic embedding. And so maybe that means that the difference between different random vectors affects the positional embedding less. I tried it with a larger number, and it looked like something like this. Let me just do it real quick. If we do this and make this, what's 16? Something like 0.04 or something like that? 0.05 would be 20, 0.06, let's say. I'm going to just make them kind of on similar scale.
Did you want 0.6 or 0.06?
Thank you. get rid of this baby. Yeah, now it gets a little noisier, doesn't it? So
One
this is,
difference with absolute position embeddings, like the sinusoidal ones from Attention Is All You Need, is that your Q and K weight matrices can select portions of those sinusoids that are faster or slower moving. It can select the lower coordinates or the higher coordinates. Because RoPE is applied later, it's always all 512 of them. But in the case of absolute embeddings, you get to pick which dimensions you bring into your Q and K
so
space.
I'm going to ask a question then. This doesn't look horrible, the additive. It doesn't look horrible relative to the rotational. But this one added it not to the Q and K, it added it to the X.
Correct.
And so I wonder if the magic sauce between the two was actually moving the position embedding into the query key rather than a difference between rotation and translation.
Well, absolute embeddings that got added at the very beginning of the model didn't perform poorly. They were used for quite a while before RoPE sort of became the more common thing. They worked fine. So it's not like there's something fundamentally wrong with them.
Okay, so this one shows that I can do kind of this decaying relative position decay, right?
Right.
I guess what it doesn't say is like, how do I make query back 10?
Yeah.
I just did a rotation matrix to do it with RoPE.
Right.
Maybe that's a lot harder with this, and I didn't play with that. Maybe that's what I needed to look at.
Yeah, it can be done. It's just not as obvious what it is, but it certainly can be done.
Okay. Let's see. Softmax, how are we doing time-wise? So 5 minutes. Do you want to just kind of run over by 10 and call this a day? We can finish this today? Or do you
I'm
want to
okay with that, but does that mean that you're going to go 5 minutes and give me 10?
What? Well,
When you say go over by 10 minutes, do you mean for your stuff or also including my stuff?
I'm assuming that we'll do the paper next week.
Okay, because I don't think the paper's enough for a full.
Oh, full session? Okay.
Yeah. I mean, I can reduce it down to as little time as you want. I can do both papers in 5 minutes.
Really?
Yeah, they're pretty simple.
Okay, how long can you extend them to though?
Yeah, that's the thing is I don't know that I can extend them to an hour and a half.
We asked Julius. He was able to get 15 out to like what about 500 or something like that?
Yeah, so 5 minutes can map out to 1 hour. That's my
Yeah. No, I think maybe I could stretch it to half an hour, but
Okay. Well then, do we want to stop here? We'll start this up next week, finish this, and then roll into your 2 5-minute papers next week? Or do you want to get them off your chest while you're prepared?
I think one of the questions is, do we have another topic for next week?
We haven't had that conversation yet, so right now, no.
Right. So
Let's stop. So let's
so
stop.
stopping means that we don't have to pick something
Okay.
as urgently. So
Before we stop, can I squeeze in one question based on what we just talked about?
Yeah.
So I looked it up and I see how they're using the RoPE rotation just on the K and Q matrices. And since those just multiply the input, isn't that equivalent? So you could rotate the input and then multiply by K and by Q. But since it's equivalent, you would just rotate them. In other words, it's less computation to sort of pre-multiply, to sort of, absorb the rotation into the K and into the Q, so you don't have to do it again. It's like it just becomes this is K for this position, this is Q for this position.
I can see the difference being though that this positional encoding especially as you go out farther, takes up a lot of, it overlaps a lot of your dimensions. The subspace of position encoding is fairly large. Like in order to get this smoothed out, I had to use 250 position. I can't have semantic information in the first 250 dimensions. So a lot of the dimensions are dedicated to position. Whereas if you put it not in your main model, but instead put it in the QK, you're only taking those dimensions from QK. Just that one instance of it. You still leave all the space for the model to use for embedding the semantics. That's just off the top of my head, one advantage.
So the other thing is that you're right that it makes absolutely no difference what goes into the first transformer layer, whether you do it at the very beginning, right when you embed, just like the original transformer, or you do it there. However, there are differences as you move on up. So because transformers are residual networks, if you did it early, it would be on the residual stream, and for example, the MLP layer would be working on the rotary embeddings plus the semantic embeddings, which maybe is a good thing. However, it would be different than the way they implement it. It also means that it would then be there for the second transformer layer, which you could argue is good. And then one of the debates would be, when you calculate values, should you apply position embeddings to them before you write them back to the residual stream, since you want everything to sort of be uniformly positionalized or whatever. Anyway, so you can see, like, I don't think it's like a completely wrong choice, but it does have implications beyond just where do you want to do the calculation. Okay. So if you decide I'm not going to write the rotations to the residual stream and I'm going to just repeat them at every layer, then it kind of makes sense the way they did it.
I could also see that the values you may not want to have rotation information in as you're pulling those forward, right? There's K, Q, and V. So the V, I can imagine you wanted to pull into whatever the context of the query was.
I think you can actually, since the values are learned, I think you could actually learn to include rotation info in your values.
But I guess my point is, you don't know ahead of time whether the key that's going to match is what position it's going to be. And you're going to want to look up the value, add it to your stream, and not have it have the position information as part of that value that you're adding into your stream. So it makes sense to me here that it is. I didn't know that, but it makes sense to me that it's in the Q and K.
Yeah, at the end of the day, it's my
belief. Was that in the
belief.
original paper? Did I miss that then in the RoFormer? It must be.
Miss that it's applied at every layer?
As it, that it's, you're saying right here. Oh, this is a comment about the paper.
That's not from the RoFormer paper.
Okay.
So I don't think they made it super explicit, but
Okay.
it is how it was done.
Gotcha.
Yeah. If you think about it, if you apply it right there when you have your queries and keys before you dot them, then you either need to find a way to write them to the residual stream so that future layers can use them, or you're going to need to do it repeated at every layer, and that's what they do.
Yeah.
Since they do nothing with values, there's no propagation of that information.
Yeah.
In the original ones, sort of the reverse of what Julius was saying, but since they apply those embeddings before even the very first layer, transformer layer, that means that those embeddings are available to all layers if they so choose.
Very cool. So I learned something out of that for sure. Anything else, Julius? Was that the only one?
Well, you just triggered a new question in my mind, because when we were talking about attention sinks, I got this feeling that each lane was sort of dedicated to each token, and that you wouldn't need rotational embedding beyond the first layer because, you're in that lane and you've, embedded for that position. And seems like it would just propagate down, but I guess, but the residual stream aspect, I guess, is maybe why you have to do it every time, because you might be skipping layers and you need to put it in the next layer. Does that make sense?
Mm, was just looking at a paper, and they talked about, it seems like early on, fairly quickly, LLMs do this thing that some people are calling detokenization. Okay, so if you have whatever, the Empire State Building, it's one concept, but it requires at least 4 words, and it might actually be more than that. If Empire requires 2 tokens, or whatever, so it might even be 5, 6, 7 tokens or whatever, but it's really one concept. And so it seems like LLMs will all do this thing where in the first few layers, Empire, State, and Building will all sort of combine into the last token position of building to give you this concept of, we're not talking about any building, we're not talking about whatever, we're talking about this particular tall building in New York City, right? And then after that, semantic things happen with processing your sentence, but it's sort of some small percentage, 5%, whatever, of your layers get allocated towards just sort of taking these English language tokens and turning them into concepts, whatever. I would not be surprised if the need for counting back token positions kind of ends at the end of that tokenization phase. And then you're mostly just comparing, where previously have I seen a noun? Where previously I've seen an adjective? Where have I seen this word before? Hey, have we talked about calculus before? Because suddenly we're talking about calculus. I want to know the last time we said calculus. So it wouldn't surprise me if numeric calculations tended to, end fairly early. But you do need them for more than just one layer. You do need them at least for a handful.
It'd be an interesting ablation study to stop doing RoPE after K layers and just see what K has to be, see how much difference it makes.
I like that. Yeah. I can imagine there's still some mechanisms that still do things, and maybe like previous token gets used still a decent amount, but I can't imagine K minus 4th token is used very often.
I can also imagine that if you're doing this at each layer, at each QK layer, that as you go higher, you might kind of shift that whole positional matrix over, that you don't need, fine resolution. At the higher levels, you're not looking for fine resolution. You want something that decays more slowly over a longer period. And there's nothing that says it, since it's only in the KQ, there's nothing that says they have to be the same for all the layers.
And then I don't think I've seen anything written about this. I'm guessing maybe this is conventional wisdom, but that if you train a transformer on the same corpus of text, but you use different position embeddings, my belief is that the transformer learns fundamentally different things because it has to calculate previous word in different ways depending on which kind of position embeddings you use. So in the end, it may still learn a concept called the previous word, but it might need to use different actual values in the Q and K matrices in order to affect that process.
The other thinking, random thought, last time when we talked about Karpathy's language models, and you mentioned the one that was the token, input token embedding was basically the character.
Yeah,
I
it's
thought
a character model instead of a word model.
Right, so it's nice, it's nice, easy to train and everything, but I was also thinking that you know, in some ways it feels like tokenization can work against you because, like you said, the odd ones you have to pull. Like if you're just using the real core words, the standard words, most popular words, that's one token, so it's kind of already embedded. But a lot of words get you have to look at a couple of tokens before you can figure out the semantic meaning of it. And also, I don't understand why at that layer I need a context window that's, you know, 8,000 or 30,000 or 100,000 long. It seems like down in there, those first few layers you were talking about that was coming up with the embedding, that should be a pretty short window that it needs.
Yeah, just like
So,
Julius was saying, what if you fiddled with not giving rope embeddings or trimming them at higher
yep,
layers? You could
yep,
do the reverse. You could say, what if my mask, how far left I can look, was significantly shortened in the first few layers? And my
yeah.
guess is both of you are right that your performance really wouldn't suffer that much if layers 1, 2, and 3 could only look back 10 words at most.
I was actually thinking a little bit different that what if layers 1, 2, and 3 get replaced with some sort of state machine, LSTM type thing that you know is evolving a state and it is evolving a learning a you know a output signal as well as the embedding and just replace those layers with something that has a short context.
Okay. Yeah, that's a cool experiment. I mean, if you want to save a little cost, you could
Yeah,
take a regular model and instead of it being 24 transformer layers, you put a little bit of LSTM there that's supposed to help you. At least we think it's going to help with detokenization. We'll see what it really does.
yeah,
And then have 20 layers of transformer. And the
right.
LSTM should be a lot cheaper than 4 transformer layers. And
Yeah,
yeah,
Albert Gu was talking about this on a podcast very recently, and he was saying that that what seems to be winning is the hybrid stuff, and he was saying that you only really need about 10% attention layers in your stack, but you need a little bit, you need some attention layers, and he also talked about this issue of tokenization, and how it's very important before you get to an attention layer, you want to get to a reasonable level of abstraction in your tokens so that there's a good nugget of meaning there.
yeah,
So, like a raw signal, a sample from an audio signal is a very small amount of information, but you take, like SoundStream or Encodec or Descript, they use a little dilated convolution
yeah,
thing like WaveNet to sort of bring it up to a level of a decent token that's probably on something like the phoneme level. And so it's a
right,
nice
right.
little chunk of audio meaning. And so Albert Gu was talking about how you really need to get to that level before you kind of go into the transformer space. And he talked about the trade-off between vocabulary size and how much there's and Karpathy talks about that trade-off too. The character thing, you need a gigantic amount of, well, you just need more layers to aggregate into words and get to that good meaning level. But then your vocabulary size is, well, I guess you have a small vocabulary, but you have and you need an enormous context buffer to get the same amount of information. So it's like I think that was the fundamental trade-off. I'm just kind of remembering this out loud. Vocabulary size traded off versus context buffer requirements.
Yep. I heard a researcher reference this paper I'm going to tell you about. I haven't found this paper, so I can't give you guys a link, just so you know. But a vanilla transformer like the original paper, it's a residual architecture, and it has an attention layer and an MLP. Okay. And they operate independent of each other. They're just adding to the residual stream or
yeah,
whatever. So what they did is they said, let's say you have a 24-layer transformer. The baseline performance is you build your vanilla 24-layer transformer, which means it goes attention MLP, attention MLP, attention MLP all the way up. They said, what if you use the exact same compute, but you're allowed to rearrange the attention and the MLP layers? And what the person referenced, and I don't know if they meant this literally or if there was some slight caveats, but they said that the highest performing model actually was do all the attentions first and do all the MLPs last. So do 24 attentions, 24 MLPs.
oh, really?
Instead of 1, 1, 1, 1, 1, 1, 1.
Wow.
Yeah. Now, again, that might be at the very edges, the first 1 or 2 layers, maybe something was different. The last 1 or 2 layers was different. But but the broad strokes was do all your attentions first, do all your MLPs later.
Well,
And,
wait a minute. Aren't the MLPs all pointwise? So you would only need one layer of MLPs because that's a completely general transformation.
Sort of. I mean, they sum to the residual stream, and then the next MLP reads it, and then it sums to the residual. And then, so there is some decomposition you could do. But yes, I think there is some variant where you have a gianter MLP instead of 24 MLPs in a row. I'm not sure exactly
think-
how that math works.
Julius, wouldn't the MLP is going to have a nonlinearity in it, right, on the output?
Yeah, but
In
it's
the middle.
Yeah.
it's
There's not one on the output?
well, I'm just saying it's a general mapping, right? By the universal approximation theorem. So, so my intuition, which, could be completely wrong, is that your attention layer sort of does this detokenization or token contextualization, however you want to think about it. So it's just this higher level concept for, this word and what it really means. And then you have an MLP to just to take that vector, which is kind of a prescribed meaning spot, and then twist it over to some other place on the hypersphere, so that, which is where you really want it for the next layer. And I don't know what's going on there, but I just think of it as just a general free map. You can take any vector to any other vector on the hypersphere. And so the attention does the conceptualization, and then the MLP does the mapping to where it wants to be for where it's going. But you don't need them in series because you already had a general mapping, right? Unless there's some other conditioning that creeps in due to the residual stream.
You're saying that because in this idea, the attention is completely separated from MLP, then it's all just one big.
Yeah, a transformer layer is an attention layer followed by an MLP. That's, and then repeat, and then so doesn't make
Do we
sense.
have reference to that paper?
Well, that's the original transformer paper.
No, I'm sorry, Ted, the one that separated those?
Yeah, I haven't found it yet. So
Okay.
Sounds pretty cool.
Julius, I mean, I think one conventional wisdom interpretation of the transformer is that attention layers copy information from other token positions into the current token position. And MLPs are not capable of doing that. So MLPs, don't take this too literally, they look up facts and append them to the residual stream based on what they see is already in the residual stream.
Oh, yeah. So they can throw everything into the attention sink if they want, right? So they have a lot of power in what
so
they.
if you see Eiffel Tower, somebody throws in it's in Paris. Somebody else throws in it's made of metal. Somebody throws in it's this tall, or it's the tallest structure in X, whatever. It was designed by so-and-so. It was built in such and such a year. It has a restaurant at top, whatever. All these things kind of get chucked onto the residual stream. And then at some point, you have to say, what is the sentence up to this point? So what is the meaning? What am I trying to do with the next token prediction? When we do these research studies, you're often predicting sort of like the last word of a sentence. But the reality is you have to also predict a lot of in-between words too, or whatever, right?
Yeah.
But if you imagine just the last word, then things get very simple because you say, the Eiffel Tower, blah, 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 was built in. Oh, let me go and crank out that year. Was designed by, and then I need a completely different thing. And also sometimes it can just be ambiguous. What was the example I heard? Anyway, so I don't think you should take it too literally, but so I don't know how that jibes with your notion of rotation along the hypersphere, but
well, I keep talking about the hypersphere only because there's going to be an RMS norm, right at the input to the next layer. So you might as well be on the hypersphere.
Yeah, so you scale it to be on the hypersphere, but where on the hypersphere you are, I think might, in my mind, intuitively my mental model is more about the fact that where I rotated it to is Eiffel Tower plus built-in 1856, or I have no idea what year, right? So it's not as much about the rotation as the fact that that rotation is equivalent to Eiffel Tower plus built-in 1856.
Hey, Ted, Chu Lin had her hand up for patiently waiting for a bit there.
Yeah. Thank you, Roger. Yeah, I was thinking that like if so if, because like the Eiffel Tower and when the linguist was built it, when it was linguist building, then it comes with like the gear, and when it was linked like on the top of it, it made links with like restaurant. So I think that may be why like if we when we encode sequence, it will encode like four words around it. It will be more easier for us to predict like what's the surrounding words, because they form kind of like meaningful things. So I think that might be work for English language, because usually it's like a four words linked with it, but like for other languages you may need to kind of like rotate to other places for like some words before.